recording. Okay. Record to computer. All right. Hello, everybody. This is nice. Okay. This is session 3 of battery knowledge transfer, where I believe we finished. We're finishing up with bus bars last time. We'll be moving on to the BMS boards further this time. We'll be continuing with our second set. Okay. So, Jake, you re-asked your question. Sorry.
What could be changed? I guess if we're moving on a 1-year.
So I think the goal, from the high level, the biggest problems that we're seeing this year is number 1, cooling, and number 2, energy capacity. Right now we can obviously go do empirical testing to see how our battery performs thermally, but ideally we would have a strong model of the real pack, and then a strong model that tells us if we change certain parameters in our battery pack design, how will that improve our cooling performance? Because as we've discussed, there are a lot of teams that do really sketchy shit to cool their battery pack. I told you guys about the fucking swamp cooler technique. Yeah. Right, they take their battery pack and right before endurance, they put it in like a 5 °C cooler, and then they drive, and it has enough. What's it? I don't know what swamp cooling is.
Swamp coolers, they do have like water pouring down, blow air to it, and water cool down the air, but evaporate the cooling.
That's boring. Anyway, okay, but yeah, so obviously there's like the big cooler. So the main thing would be, yeah, having an actual, because right now we've been doing our best effort this year to try to get a simulation that can work to model the thermals of the battery pack, and that had issues. We tried to do empirical testing, and the empirical testing has yielded results, but obviously scaling up results from a small scale empirical test to a large scale empirical test has some amount of error. But ideally, we'd be able to try different parameters for a pack. Let's say we wanted to change the spacing between the cells. Let's say we want to change the cell orientation. Let's say we want to blow air across them in a different direction. Ideally, we'd be able to have a way to test, does that actually make your performance better, before we just fucking send it? Because that was a big thing that this year we came in and the pack design's already done. We have to deal with what we have. But ideally, we'd be able to come up with multiple alternative designs, because our pack design right now looks like cooling is really hard. It's in our best scenario, maybe almost acceptable. And that's using reasonable estimates and approximations. So anyway, that's number 1 thing. And then number 2 is it's just so fucking, our battery pack wastes a lot of space. And I don't know if you've ever talked to Ben Barbaro, but he has experienced so much pain, both with Drew and Isabella and Jake and Ben Barbaro have all been involved in the absolutely painful process that was being able to fit the accumulator into the frame. And it's we had the SES issues with the mounts, and there's just so many issues where everything needs to be stretched in. The battery pack is so tight right now that our tolerance is really tight. So ideally what we would do is you'd be able to sort of go through and redesign it to, even if you change nothing electrically, just restructure how it's approached mechanically, to make it more compact, both to improve your cooling your cooling capabilities, whatever method you use, and then similarly to actually make it smaller and make sure that it fits in the frame that we have. Because right now, as you can see, our battery is really poorly placed, that it's actually really far forward, but it doesn't fit well onto the firewall, but it also doesn't go back super far, but it could get way closer to the diff. And it also means our motor sits exactly 1 inch away from the battery, which is stupid. And so we have a bunch of just annoying stuff that comes out of the battery being really big, because we made it big because we didn't know that we had to make it smaller. And so now the idea is, if we can push the battery to be lower, if we can push it to be denser, and we can push it to get out of the way of the motor, fit more effectively under the firewall, that can make packaging, make mounting so much easier. And then obviously the same thing from the electrical side of things. So if you're already going to go through the effort of reorienting the whole pack, electrical side of it would ideally have a big hand in saying, okay, well, what are ways that we could potentially change or improve the battery pack to make it even better? It's basically, however much bandwidth you have to be able to make changes and improvements to the battery pack, go for it. Our battery pack is bad, and any ways that you can radically make it better is great. Don't just take our design and make minor changes to it year over year, because fundamentally our design is not a design that you should be copying. This is a design that works, not a design that's good. But it does look pretty nice.
This describes a lot of stuff.
Yeah.
What specific?
Yes. So the electrical side is something that we right now still do not have the information necessary to tell us what changes we want to make electrically. The reason I say that is because our best models right now for how much energy we're going to consume are all from simulation, which Ben has run using stuff like LapSim, OptiMap, whatever part of that. And while those are great, those are fundamentally simulation tools that are not our real drivers in the real world doing real world things. And so what we would have to do is go out into the real world, run these tests, and see how accurately they actually match up to the simulations, and then take a look fundamentally electrically at the battery pack and say, is our battery pack even designed for the right goals in mind? Because if it turns out that no matter what we do thermally, we cannot keep up with a battery, like let's say we say water cooling is impossible and we have to do air cooling, fundamentally us having a battery pack that can output 80 kilowatts of power makes 0 sense because of the fact that, oh my gosh, we can never cool 80 kilowatts of power anyway. And so then electrically, you could rethink, okay, how are we selecting cells? How are we packaging cells? What configuration are we using? You can reorient that to say, okay, how do we reconfigure this to target a new peak power output that matches what our thermal abilities are?
First, when you said the capacity is like one of the things we're worried about. You did mention earlier that our battery capacity kilowatt hours is actually greater than most other teams.
Yes.
Is it just because it became so heavy that we don't get enough range out of it?
That is still an open question that I'm hoping we can have the answer for you by the end of competitions. And that's why, like right now, all I can do is speculate for you, and I can't tell you the answer. And that's something that I will be graduating at the same time as we're figuring out the answer to that. Is you're right, there is fundamentally some weird disconnect that there are great teams out there that are running awesome times in endurance that are using like a 5-point-something kilowatt hour battery pack, and ours is, like I said, 60% bigger than that, and somehow our models say that we're going to run it slower and still run out of energy. That could mean that our models are inaccurate. That could mean that our vehicle is inefficient. It could mean that our battery pack is generating so much heat that it's just dumping energy. Or it could mean that those teams have really light cars and they have really smart drivers that know how to drive it better than our best simulation tools use right now. Because our simulation tools try to go as fast as possible, not be as efficient as possible. And so that could be a way to think about it is maybe we need to come up with our own simulation or modify an existing simulation tool to really say, how do we most efficiently drive to go as fast as possible? Because I believe right now the tools basically just say, drive as fast as possible and then give us some power limits if you need to. And that's how Ben's been able to tweak it. But ideally, it would be working with Ben, doing our own testing and figuring out, okay, are we just stupid and 5 kilowatt hours is enough? Or are we right and every other team is sandbagging except for the cars that weigh 300 pounds and are made exclusively of carbon fiber? We don't know. And that is ideally something that we'd be able to figure out as we finish this year and as we go to college.
Also, like, is it possible to split the accumulator? I mean, it's a massive box in the middle of the car right now.
So the answer is yes. You are by rules allowed to have as many accumulator containers as you want. The rules even explicitly says like, hey, you can have multiple accumulator containers. The only downside is, you know how we talked about you want to do the minimum number of segments possible because there's overhead that comes with that. Every accumulator container has a similar level of overhead. Of now you have what are called AIRs, contactors, basically big mechanical type switches that connect and disconnect the battery from the rest of the vehicle. And you have the main battery management system board that has to handle into all that interaction. You have the big connector that goes on there. You have all the pre-charge resistor that basically makes sure that when you turn the car on and off, it slowly rises up and down to the voltages that it's at, and it doesn't just instantly spike to 600. You have all this extra overhead. So if you find a design that actually breaks the battery into 2 parts, sick. But fundamentally, what most teams end up finding is it's better to make one weird shaped accumulator rather than 2 separate accumulators, just because of that. But if you can find a design that uses 2 or 5 or whatever, totally go for it. I support it. I know nothing about cooling. If that's right, cool. I believe you. I don't know anything, so nice. But like, yeah, so if that's easier to cool that, then like, cool, maybe that would be a good approach to say, hey, cooling is a big problem for us. Let's consider splitting it into 2. And then the question would become packaging of like, how do we actually package this? Because it still has to be separated from the battery by wire.
How much do people want to talk other teams?
Like us 2 other teams?
Yeah, or other teams do not. Like, could we get frame of reference for
how they're able to put down such confined smaller batteries? Like, will they tell us like, oh, the water cooler, they're super light, and like, how much will this be?
Yeah, so it will drastically depend on the team. Like obviously the actual neither of you have been to competition. None of you have been to competition. Yeah, you've been. The structure is literally like, imagine a fucking parking lot, and then you like have every parking space. You pull in and you put up a tent, and then like that's where you do your shit. Like your car sits there, all your work goes there, all the tooling is there, everything, it all fits in that one parking space. And then your truck with the trailer is in the next parking space. And like that's the space you get. And then right next to you on either side, there's another team. Usually some of those teams might be really bad, or those teams might be really good. It's like somewhat arbitrary what teams will happen to be next to you. It's not like you're placed next to like other bad teams or other good. And so what'll happen all the time is you'll find some teams that are really nice that you can literally go over to them and be like, hey, how's your car work? They'll just sort of wander around, like, and you'll have that happen to us sometimes where people will wander up to our tent and be like, hey, you sort of tell me about your car. What are you doing? What's cool about your car? And last year we were like, oh, look at our 3D printed titanium exhaust. And they'd be like, whoa, does your car run? And we're like, maybe. So we can, and people will go and they'll ask questions. There are other teams that are total fucking assholes. And you'll go ask and you'll go talk to them. And then they're like, specifically, I don't remember what the name of the school is. And if you do remember it, don't say it. There was one school that had like how for us, our faculty advisor doesn't really do anything. Beltran just sort of like lets us do our thing, which is awesome. We get to run ourselves independently. There are some teams where the faculty advisor is like super in there, like helping with design reviews, actively is basically the PM for the team, is doing all the purchasing. They're like, that is their thing. And it means they get super defensive and protective of all the stuff. And so, if they see another team doing sketchy shit, they'll like go call it out, and they'll go find judges to like call you out and say you're breaking rules. And if you go to try to ask them questions, they'll be like, no, get the fuck out of here. I'm going to report you for. So you'll find some teams that are assholes and some teams that are super nice, and it'll be hit or miss. But it's actually recommended, especially for days where there is work to be done, but not by you during comp. Yeah, just go roam around, talk to people, ask questions. Especially if you've had a project on the car, go ask them how did they do your project, because you will know the problems that they faced. That's one of the great parts about us using parts that other teams use, is you can go find, because how we use the MRAX 228 motor. You can literally look around a competition. I guarantee you half of the teams will have the exact same fucking motor, the MRAX 228 high voltage liquid cooled, guaranteed. High voltage or medium voltage. And so like that's the thing. You look around, you'll find a bunch of teams that have that. So you can go look at it. You can go ask them, be like, hey, how'd you do this? There's a bunch of teams that I've seen online that have cool jigs that hold the differential and the motor in one jig, rather than having two separate jigs for it. And then you can jig that to the frame, and then it just floats as a body in the rear. And then that's how the diff mounts can also become the rear impact. And you can have these whole cool complex designs that can solve this problem. So sometimes all it takes is wandering around, but sometimes people will be asking. So basically, it's like being a normal human. Cool. No question. All right. So it sounds like we were finishing up with bus bars last time, but it sounds like I kind of skimmed over the BMS sensing connection stuff a little bit. So I'll kind of rehash on that a bit before we jump into the actual BMS board mounting itself. Okay, so yeah, the main thing is, as a reminder, bus bars. What are bus bars? Who wants to explain to me what a bus bar is? No, fuck you. You both worked on the battery. No, okay. You're working on the battery. One of you. That's fine. Okay, fine. We'll take it. Piece of metal. We'll take that. That could be the bonds too, but we'll take that description. Yeah, a piece of metal that connects the cells to you. Yeah, and so the idea is, you have these bus bars, and we had all sorts of problems because we epoxied them, and they were pretty small, and they were made of copper, and then getting them plated was really hard. And one of the big things that we talked about a little bit last time is the fact that we have these BMS sensing PCBs. Like I mentioned, oh fuck, I didn't bring one up. We have fully assembled segments. Do you want to go fetch one? Actually, can you go fetch one? Can one of you two go fetch one? Because you know how to actually pick them up. Sorry. One of the fully assembled. So 2 or 4. If you'd like, yeah. Leaves. Yeah. Yeah, okay, so the big thing with the BMS sensing PCBs is that fundamentally the way that we had to do our battery management sensing stuff is kind of funky. So remember, we have 3 actual things that we have to do from the battery management system. Number 1, we have to check the voltages. Number 2, we have to make sure that the voltages of each battery cell don't go above some threshold. And number 3, we have to check the temperature. Ideally, in our battery pack, we would have some super easy way that you could just detect all this really easily with like no wiring, and it'd be super compact and ultra easy to disassemble, but that's not how it's going to probably fucking work, and you're going to have some problem. But the way that we did it this year is we didn't think about that. We were like, we'll just wire it ambiguously. Like I said, we were going to do some sketchy shit where we like took a nickel strip and then spot welded that to the bus bar and then soldered a fuse to the nickel strip and then soldered a wire to the other end of the fuse and then heat shrink over that. Very sketchy. And so instead, to make it less sketch, we did these full custom designed PCBs that sit on top of the bus bars. But those had a lot of problems where it's like the fuse now needs to go along the side of the PCB, because if you put it on top, it's actually too tall and stands above the standoffs, which sucks. So we had to put it on the side, which means soldering it was weird. Second thing is that PCBs, we didn't tell Hef how to bond our battery pack. And because of that, it meant that the bonds were kind of just like wherever on the bus bars. So we had to make these super skinny, fettuccine looking ass PCBs that run right down a super thin strip in our battery pack to avoid all the bonds. And ideally, in the end, we would just have a PCB that sits ideally next to one of the bus bars, or maybe somehow it's the bus bar itself. I don't know. There are companies that can do that apparently. Where we'd be able to have a really simple, easy, integrated from the start solution for how we actually get to the connections on it. Like I said, don't assume, ideally, if you can at all costs, avoid all wiring. All wire. Literally, if there is a single wire, try to not use it if possible. The reason I say that is because let's say you want to use one wire to detect every voltage. There are 140 unique voltages you now have to sense in the battery pack. And that means there are now 280 unique crimps that you need to manually do by hand. And 140 wires you need to cut out to length and strip by hand, which sucks. That's what I've been doing for the last 4 days. So instead, if at all possible, you would try to make some other solution. Maybe you can buy a ribbon cable that already does it for you innately. Maybe you can design your board such that one board sits here and another board sits here, and they actually just plug into each other directly with connectors, and there's no cable. I don't know what is the best solution for it, but I do know some way to make it such that, or maybe you can have your bus bars directly stick into the PCB so it can natively sense all of it. You just have temperatures. I don't know what is the best solution, but I do know putting thought into saying, okay, how exactly are we going to connect these sensing connections from BMS? Where do we put the BMS board? If we're going to do sensing boards, where do they go? If we're going to do sensing wires, where do they go? How much effort is that going to be? How much cost is that going to be? And then, yeah, so one of the things that I mentioned in here is that the easiest design would probably be doing a custom PCB that bolts into the cell holder itself, and then they could bond directly from the bus bar to that custom PCB. When I say custom PCB, I know you two. Do you know what PCB stands for? Okay, yeah, okay, cool. You know what it means. Cool. And so, yeah, that's the idea. Is just making sure we can design something, put it in there, make it basically put in extra design effort from the beginning to reduce ass effort at the end, because that's what we're sort of reaping the sucky rewards of right now. We didn't put a lot of effort in the beginning to pre-plan everything, and now I'm spending, the 8, 10, 12 hours a day wiring up each battery segment at a time. And it's a huge time sink, and it leads to a lot of potential failures. Like if I make one mistake and I don't miss it during my QC process, I can damage the battery. I can damage the BMS boards, which are hundreds of dollars a piece. And ideally, you would minimize the chances, the number of things you manufacture to minimize the risk of failure. It's your FMEA stuff.
When you say I'm like a massive bus bar instead of one, how do you connect that to capital? Like I don't know electrical well enough to understand what you're saying.
Okay, so let's see. How do I describe this? You have the segment. Oh, you brought one of the kids.
Segment also brought sense board and harness piece and BMS.
Oh my god! Wow. Okay, let me let me stop the share really quick so that way I can show off stuff to the screen. Hello, recording. This is me today. Child,
The big scary boy.
okay. So, for example, what I'm showing off right now to the class is the fact that this is one of the examples. The lid isn't on properly, but this is one of the examples of one of our battery packs, where you see we have all of this wiring on the top that has to adapt, going from the sensing PCBs. I assume you guys can see it on the projector, so when I show it here, you can see it there. That's fine. Yes, the idea is that here we have the actual, we have the battery cells themselves. We have the bus bars that go in between them with the bonds going between all of those bus bars to the cells. And then we have these custom PCBs. We have these custom PCBs that are designed, and then they're actually like conductive epoxied onto the bus bars, which is super sketchy. Don't ever do this in the future. It sucks. But yeah, don't ever do this. But we basically use like electrically conductive, like silver-based epoxy to goop the bus bar, these custom PCBs on. And then the big thing of effort has been that, number one, I need to then, not only do I need to assemble those PCBs, I need to assemble these custom wiring harnesses that you see on the top, where you see you have, I think it's 32 wires with 64 unique connections on either side. So that's 64 wires, 128 crimped connections on every single segment. And so it takes me, who's pretty experienced in harness design, about 2 hours to crimp one of these guys. So it's about a 4 to 5 hour process for the whole thing when you include installing it, testing it, making sure all the voltages make sense, make sure it didn't mess up any of the connections. So it's a pretty slow process. And then I guess the last thing I'll call out that's pretty simple is that these 2 big red plugs in the middle, those are the actual like power connections in the pack. Those are the maintenance plugs. And that's something that I know we highlighted. Maybe we already covered, I don't remember. But did we cover maintenance plugs already? Yeah. And so the big thing is like, obviously it's pretty easy to say, okay, cool, let's bake the maintenance plugs into the battery pack. Because obviously right now, the way that we're doing it is that these had to be like retrofitted onto an existing design because of a change up in the part that we're using last second. So cool. Basically you can see we've had to go through like a lot of physical effort. Of the chances that I mess up a single wire in here is very high. And there are significant consequences if I don't check that, find that during the testing process. Like, all I need is to short the wrong 2 things together, and then I can either damage the battery, damage the BMS board, or worse. So yep, that's what's going on. That's the segment. Any questions about it? What's up?
Do you think we'll continue using things?
I think that I was not able to find a better option.
Other models.
Yes. Oh, yes, I should clarify. There are different versions of this plug that come in both different sizes, as well as different types of terminal things on the bottom. Like you have a screw terminal, you have like this bus bar terminal that we cut up. So there are many different options, and it would definitely be open to picking different ones, designing different ones. Amphenol is relatively open to sponsoring us with parts.
Also, I feel finding a way. These ones we have stuff right, so we have to like cut them up and drill holes and fit a huge pain in the ass out of machine copper. So finding one that you can use off the shelf exactly how it is, because machining copper is.
Yep, exactly. Just ideally something off the shelf, easy, works, plug and play, modify as few things as possible. One of the biggest things that there's a bunch of different websites that give a lot of great advice about Formula SAE. One of them is called designjudges.com. And if you go on there, a lot of their big commentary about, hey, how do you start a formula team? What do you do when you're making big changes on a formula team? One of the things they say is, if you are new, you are an integrator, not a designer. And that sucks because it makes you feel shitty because you're not actually designing things. But what you're designing is a system. You're not designing a part. And so if you can buy as many things off the shelf as you can afford and integrate them together to save you engineering time, do that. Only when you have more bandwidth or have a need that drives you to go outside of that, meaning you either don't have the budget or there isn't a part that does what you want, only then should you design it yourself. Obviously, that fundamentally clashes with a lot of our principles of education first as a team. And so we always will bias towards, let's do the thing that's more educational, even if it takes more time and more hours. And that's a balance this team is always walking. of how do we make sure we're effectively and efficiently using our time? For example, do we have someone else weld our frame versus us weld our frame? Like, how do we want to use our time efficiently versus money? And are those skills something that are really valuable and something we want to cherish? Or are those skills just skills that we would not mind if we did? And so that's always there's lots of topics of conversation. For example, all of our PCBs could actually get assembled out of house and they would be perfect. But that also means that they would be way more expensive and they would have a much longer lead time. And we're not learning about them. Cool. I will take, what's up?
For our future battery pack designs, do you think we should be like engineering around?
Should we should you engineer around the current BMS shape? The current BMS has been designed as a little rectangle that is already pretty skinny relative to the height of the battery itself. I am going to strongly assume that most of your future battery designs will already follow a shape where one of the faces will be able to fit these existing BMS boards. The main complexity will more come that if you change your segment design to say, okay, let's now have 23 in series per segment and then 4 in parallel, and you're now dropping your peak voltage by a little bit. The main, like you could see some advantages of that of moving down to 6 segments and then you can spin it around to different directions. The current BMS boards cannot do that because they cannot sense as many, they are not currently configured to sense as many voltages as that would require. Same thing, they don't have enough temperature sensors to measure the number of cells that you would need to do a BMS board change. So my response would be, if the team does not feel confident in their ability to meaningfully redesign these BMS boards, then I'd say try to design in mind of let's use the same boards and keep them. If the team has someone who is sufficiently interested in designing a BMS board, I think it would be great to enable and support someone going in to try to make a meaningful revision to it and get that knowledge transferred on. Because if someone works on it next year, that's the best chance of someone actually transferring the knowledge from Joshua into a new person. Because fundamentally, if someone doesn't do it next year, then that means no one's going to do it the following year. And it's going to basically just become a purchase part at that point that we're making ourselves that we don't understand. And at that point, it's like, well, we went through all the effort of designing it. Once we have all the design documentation, we might as well actually use it and modify it. But that would only be if we have someone smart enough who's willing to take on the challenge and actually meaningfully changing it to meet the requirements. Cool. Any other questions?
What's like the difference between BMS?
So if you want a BMS that the super high level TLDR is to buy a BMS that does what we want, it's really expensive. We looked at it. You can buy what's called the most common one in Formula SAE is the Orion BMS. I think it's like $2,500 to $3,000 or more, depending on what configuration you get.
Yeah, it's like, I think it also might be a single centralized thing that has to sense all of them instead of distributed.
Yes.
And so you get like this whole big aluminum box that has stuff inside that you have to figure out how to talk to that will do your BMS things somehow. And it has a bunch of sense wires that you have to plug into it. And like it's entirely possible to use, but it's expensive and somewhat proprietary. There's like a computer that you can configure it. And so it isn't really the ideal solution for us, and it's really expensive. Where this, we have full control over the code. It was a lot of effort to get it working, but we have full control over exactly how it works. It's a distributed system that doesn't need to take up as much room, I think, as the Orion BMS would.
Yes.
Because we're able to just have like the circuit board embedded in the pack instead of a completely separate ball.
Yeah. So the TLDR is we get a way better, we get functionally, at minimum, we get something that is functionally equivalent, if not from what I've heard from other teams who work with the Orion, we get a actually way better solution that is also custom built for our pack, for our solution. The only downside is
they are complicated and they are hard to work on them. Joshua put a lot of time and effort into making them work, and they're very complicated. I do believe this team has the brains of the people here to be able to actually update them, revise them meaningfully. But I do think that would be a significant undertaking, and someone have to be that would be their whole year project of is it worth changing the segment design and going through a BMS? So revising the BMS will be a lot.
yes, definitely. And it's also you will be available as an alumni as a resource. So while you will not be able to directly debug the code for them, it will be something that's available to say, hey, maybe this is the problem, maybe this is the problem. You can get on a call for an hour or two and potentially walk through getting a solution. Or just explaining why the board does what it does. So.
What is the code? Is it the note interface? I don't know.
So the BMS, each board, we use a TI chip on it that can monitor the voltages and temperatures of whatever's connected to it, but it has to be configured by accessing the registers directly in the chip. And the interface to talk to it is you use they have a data sheet that explains how you can talk to it over we're using UART in order to access the registers. It uses a proprietary communications protocol for between the chips so that it's fully isolated, because we need galvanic isolation so that we don't have 600 volts going into the LV system. And so you directly access register to read the voltage. The code, at a high level, the code you call EMS.get voltages, but that calls code that also is custom written. I wrote it, that goes in and says, okay, I am going to use the VQ communication, send the UART communication to do a stacked read of voltage register 0 of length, however many voltage registers I want to get all of them, and then parse them. And so it goes very low level, but then at a higher level, the code reads in all the voltages, reads in all the temperatures, spits them out over CAN, and does some safety checking and turns off the car if something's going wrong. I don't know if that answered your question how you want it.
Yeah. Cool. Any other? So yeah, one thing I guess I wanted to mention is that in this slide deck, I'm focusing on battery stuff. So if you are interested in BMS stuff, learning how that works, I will not be focusing on that because that is fundamentally Joshua's thing. He can explain that way better than I can. And if there are multiple people who are interested in actually taking on BMS project next year, and whether it's just from a software perspective or a software and hardware perspective, doesn't matter. If there's anyone interested in doing that, I would recommend you coordinating with Joshua on however you learn best. If that's just he speaks and you listen, or if that's a slide deck or something. Because all I'll present here is how we mounted it. And I won't really dig into the details of exactly what it what it looks like to design a BMS board, because this focuses mainly on just the back. Yeah, great comments, great thoughts. Cool. Make a BMS knowledge transfer channel. Cool. Okay. Continue. All right. Now we'll get to our first slide of the day. Okay. All right. We finished bus bars. Let's get to the BMS board. Like I mentioned, I won't be talking about I won't actually explain the design of the BMS board in this meeting. Instead, I'm going to be talking about how we actually mount it in the battery pack right now. And honestly, it's super simple. Literally, we just need to have a way to rigidly mount it. Obviously, we can't have the battery pack just flopping around in there. I guess you could probably tape it in place, but maybe don't do that to the system to make sure your car doesn't explode. Right now, the way that we do it, actually, if you guys want to look at, you can come up and look at it in the battery pack itself. We literally just have a set of little shells that stick off the side of each of the cell holders. And then we'll set a little shelf that stick on the side of each of the cell holders. And then there's essentially two little thin plastic spacers that are sitting in between the board and then just the other side. And that's it. It holds the board very rigidly in place and it maintains all the spacing and height and all that stuff.
So this is standard. Yeah, so they're just tiny little 3D parts.
Oh, so that was like the 5 foot.
Yep. And so the thing is, these are very simple, very straightforward process of how we sort of mount it. The big thing that I sort of am highlighting here is it's like, yeah, you basically just like need to mount it, and you need to have at least some amount of space up here to have wiring. As you can see here, we left like a buck ton because of stupid. And ideally, well, because there were multiple confounding factors that led us to have higher spacing, and it turns out both of those factors went away. So ideally, in future designs, we would be able to shrink this. Yeah, because one of the big reasons we actually picked these particular connectors, the Hydro EF11 connectors, is because they are both very thin, dense, so you can make them super small, and they come with a they're pretty short vertically, and they come with a right angle connector option. And so and they have both male and female headers that you can solder directly into boards. So if you wanted, you can plug board directly into board, which is nice. And same thing, you also, I think our total height, if you do like a right angle connector, you can get it to be only 15 millimeters off of the head of the top of the BMS board. I think right now this is like 1.5 inches or so, like maybe 1 inch to 1.5 inches off from the head of the BMS board. So you could shrink that down like a centimeter or more. And if you got even craftier where you like have the BMS board hang off the sides and the connector plug down, I'm sure you can shrink that more if you wanted to get crafty, if someone's willing to go into that depth for a BMS board design.
Why did you like stop the whole here? Like, why don't we have a hole on this side?
So, problem. This battery pack is super fucking dense. If I try to push air through it, it doesn't like that. This is not very dense. If I try to push air through this, air loves going through here. If you have a resistor with a really low value and a resistor with a really high value, all the air just goes up here. You struggle to generate power. And so we try to limit the number. That's why this side is flipped upside down.
Well, that's flipped upside down.
And that's why you can actually see, that's why we cut them up. We actually, I think, are going to even take parts of these holes over based on what I heard that somewhere. And so that we can really make sure we do need some airflow because the BMS does generate very interesting. But the idea is that we do need a little bit of airflow, but we don't want to shove too much in because then we're just like dumping all of our fucking air pressure through an open channel. And
So that's just a mistake.
this side is just flipped.
Yeah.
Oh, I see.
And when I was putting it together,
I have a question. Why was gluing these together like this? This has to be.
let me actually pop it open, stop share. Okay. Cool. What's
Like,
up?
Why is this? Why are these not?
Why are the gaps on the other side not symmetrical?
Yeah.
The standoff heights.
Oh, that.
This is actually the wrong way around because once again, stupid. But the idea is
Oh, okay,
the,
that makes sense.
yeah, the wider gap is good.
Okay. I was just noticing that.
Yeah, no. And so that's why we have the different hole spacings, and so you can have holes and holes on it.
The BMS might dissipate like 8 to 10 watts while charging.
That's quite a bit. And so yeah, that's why we have a little bit of airflow for the guy. We don't need
Then again,
need
that's
fucking
not that much compared to under load.
yeah compared to the 14 kilowatts of heat we produce at load. And so that's the whole thing.
In theory, the problem with taking the holes and while charging, it's like the meshing off.
What's
What's that?
with the blue?
That's a thermistor. So
Yes.
it's not butane, it's like a little piece of blue silicone with a little resistor at the end, and the resistor changes based on temperature. So those are our temperature sensors.
Oh, I see.
Are these mounted right now? Oh,
They're sort of mounted.
Yeah, this lid is
Don't
like
bake on them, but like you can pull off.
this lid is not for these.
Actually, don't pull off the red plastic because then you have.
because I said there's like a screw hole looking thing. I don't think the screw is.
No, it's because these are.
Not fully-
This is the like a thing I cut because it
Got it. So like it screws in from the top.
Louis would be the person to ask about that. I gotta be honest.
Okay.
I don't know the exact details. Yeah, no, the top has to be removable so that we can access the data.
Well, so this is still like the actual thing is like not clear, right?
Yeah, sadly, the real one is, at least as of current, the only material we could buy on McMaster was CPVC or high temperature PVC, and it kind of sucks. So, if someone else wants to volunteer to go find us a UL 94 V0 rate flameproof material.
It's really expensive.
Gluing is just.
Yeah. So like, is it? So are all of the corners gonna be glued together?
All
Is
the
it talk like this then?
It dissolves the
Your
material.
stuff is really expensive.
It's
Mhm.
like, it's
Louis,
Then we put like RGB
do we
LEDs
bolt
in it.
this?
huge.
Are there gonna be bolts in here on the real one? Nope. Nope.
So
Okay.
But how for the main plugs?
the
Mechanically not.
This one, this guy,
From pushing down on them?
big.
Pulling up.
Does it deform the surface to scratch?
No, it doesn't like.
With the handles?
It's more like slimy.
So when you.
But like.
Skip forward like 5 minutes from now, when we're done talking, whatever's going on. It's exciting then.
Pulling
Yeah, like I was
goes into the lid.
Oh, actually, I guess I can give a recountment of what we talked about. They're talking about why it's a pain being able to assemble the e-boxes, so this clear box, out of the new material. So this material existing is polycarbonate,
So the issue.
which the problem is that polycarbonate needs a certain thickness of material to meet the flame rating that we need in the battery pack. All battery pack insulation needs to meet UL 94-V0 flame rating, whatever. It means it like self-extinguishes in 15 seconds or less. And that's a rules requirement. Polycarbonate doesn't meet that for this thickness of material. This is 8-inch thick material. So the only thing we could find on McMaster that was the right thickness is CPVC or high temperature PVC, chlorinated PVC, I think. And what they were talking about is that securing the joints together, because the edges are just two edges of a sheet that we then try to use like an adhesive that melts the base material and bonds them together. They were expressing that adhesive that they were using was not great because it sets so quickly. That's one of the major challenges with the new material, where we've considered, okay, maybe do we want to pivot to a different UL 94V0 rated material? Is that cost effective, and do we have the time for that? The other side of the conversation that's happening right now between Joshua and Louis is talking about the idea of if we want to mechanically mount the actual maintenance plugs. So right now, the way the maintenance plugs work is that there are two big like bus bars that are on the end with a hole in them, and then we actually have like a little squiggly thick copper adapter that bolts from that bus bar directly into our maintenance plug, or like our main contact for the segment. It's pretty robust, but it is still just the electrical connection. So when you plug it in and out, you're putting all of that load directly into the copper bus bar, which isn't great because you're loading connections that are intended to be loaded. So yeah, it can lead to lots of wiggling, lead to lots of issues. So there is currently a conversation going on about are they comfortable with leaving it this way, or we plug it, unplug it, and just more careful? Or are they comfortable with the idea of trying to move over to use something like where we bolt it to the lid? Because that comes with other complexities of how you would attach a fastener. So yeah, those are the conversations that are going on right now. Some of the things that were discussed is how airflow works through the actual segment. It's the fact that we have decided done wrong. But the idea is that there are a lot of airflows along the main part of the segment, and then only a few airflow holes, don't worry about it, at the top. And the idea is that few airflow holes at the top are to make sure that you have less air flowing across the BMS. Because since the BMS is just open air, it basically all of our airflow from the fans ends up going through there, and it allows us. It makes it really difficult for us to build pressure in the pack to actually get air to run through the battery cells. Cool.
Again, it's not, in a pulling.
Why are there like not that
Yeah,
many?
people are pushing.
Well, in a pushing motion, I wanted.
A lot of temperature sensors, yeah. So according to the rules, we have to sense the temperatures of at least 20% of the cells in the battery pack. Yes. So if you do that math out, we have 80 cells in this segment, and we need 16 temperature sensors. So we have 16 temperature sensors, 8 on either side. That's exactly right. They do ask that you make them that like every cell should be sensed from the perspective of you're at least close to every cell. You don't want to just put all of them over in the corner. And so that was actually one of the big things is that in the original design that we submitted, we put 25% of them, but then I talked to Joshua and actually it turns out I misremembered, and we actually could only do 16 temperature sensing. So we had to redo our organization of temperature sensing to make sure that we could distribute the 16 of them evenly, to make sure we have a fair number of connections on either side of the pack, to make sure we're getting a good temperature sensing on both sides, as well as evenly distributed in pockets.
Why does
I'm very much, if anybody wants to go to the effort of designing something to.
Why?
support
Yeah,
this,
so your question, why is PCB epoxy done? What
if-
other approach would you use to connect it?
Especially.
Screws? Where?
like solder?
Screw can't solder to the bus bars. That, what is the bus bar sitting on?
Oh, yeah.
Oh.
So something like this, but not.
Yeah.
Actually, when the BMS try and make it,
Yeah.
then it's
Like,
like.
and then like at the bottom.
But yeah, so
where you-
there's a bunch of things, is that, yeah, if you
Square, right?
design, like, remember, these cell holders were designed with no sensing in place. And so if you were to design this in mind to say, hey, I want to do my sensing connected, then what you can do is you can say, hey, what if I have a strip along the side that has a PCB and then there's bolt holes that I can actually bolt into it to mechanically fasten it? And then I could have the bonding company actually bond directly from the PCB. That'd be way easier. And like, if we were intelligent and planned it out from the beginning, we could have done it, but we didn't.
Since PCBs replaced the
What's up?
On this pod and this pod, you can fit in probably like an M1 or M2,
In where?
like
Between the cells?
between
I'm not
the
against,
these
I'm not
gaps.
against.
You
I know,
can,
like,
Like
you have to
that.
drill it.
you
I'm
can
just
fit,
like-
yeah, so we actually did the math out. You can fit an M2. I think you even fit, if you get lucky, up to an M2 point, depending on your spacing, an M2.5 bolt in there. The main challenge isn't actually the bolt thread itself. It's the fact that you don't want to just thread your bolt into like nylon, because that'll strip really quickly if you keep doing it. So the idea is that you would like to put something like a heat set insert in there, but there's a number of issues with heat set inserts. Number one, a heat set insert fundamentally is melting the material around it, which means if you do that too near to battery cells, you're getting them pretty hot, you're deforming the cell holder. And the big issue is that a lot of the time when you're doing a heat set insert, you won't get it perfectly aligned. It can go a little bit off, which you can compensate for with clearances. The other thing is that generally it's pretty common if you don't spec your hole well, you'll actually get a little bit of like a mushroom top that'll happen around the edge where it'll like push up material. You can design your holes to not do that, or you could do a post-processing step where you like cut that off. But that's actually one of the things that HEX, at least for bus bar mounting, highlighted that they would be against the idea. It would be worth us asking them to be like, hey, can you confirm this interpretation of your documentation? But at least according to my interpretation of what their documents they gave to us say, they say that they do not recommend any form of heat set insert because of that doming. They found that they are prone to wobble up and down.
What if you use, oh, that makes sense.
Yeah.
What if you use
Plastic screws.
Yeah, but they won't head out the nylon already.
Maybe that's the solution.
You think what?
Yeah, and so that's the thing is, it's like, I don't know. I haven't thought of the solution space for these problems is so large that I am nowhere near close. None of us are to having thought of all the possible solutions. So, and I would even encourage you to think bigger rather than looking and saying, this is a problem, let me solve the problem. Look and say, is the design fundamentally flawed, and can I improve the design to remove the fundamental flaw? That may not be possible, but it may be possible in some ways. So rather than just saying, I have problem, fix it with hammer, see if you can remove the need for the hammer. For mechanical fastening, that might not be possible. But for other stuff, that may be a property. So, no idea. Literally, I know nothing. I know that there are some teams that run pouch cells, and if you want to hear more about pouch cells, you have to go to Europe. The big thing that I want to also harp on about pouch cells is that while they're super sick nasty, they are easier with the European rule set than with the American rule set. There are some rules from my conversations with some of the people at some of the best teams at the European Formula student teams. Their rule set is similar, but not identical to ours, is my understanding. And there are a few rules that are like super annoying for us that they're like super don't have to deal with. So it may be worth investigating. Okay, cool. Maybe my understanding is wrong, and maybe they have the exact same rules as us, and maybe they've solved those problems, or maybe they do have a slightly different rule set, and they are able to use pouch cells so readily because of the fact that they don't have rules that we do. Don't know. So, cool. Question. I appreciate that we covered one slide.
Oh, yeah.
Woo! What's up? We covered a lot of cool stuff. What's up, Chloe? Okay. Okay. All right.
One hour later.
Howdy, y'all. What's up? So, it depends on how badly you fuck up, but the vast majority of our PCBs and our battery pack is designed to have fusing as an intricate part directly at the source of the power. So if you were to put like a dead short between two battery cells, unless you really get crafty with it, generally what should happen is that those bonds on the cells should all heat up and break before the batteries get significant. Our batteries will run out of spec with this current bonding configuration. But ideally it should still break before the battery cells like completely. Same thing with the BME, same thing with the PCBs. The PCBs actually have like a contact on the bottom and then immediately go into a fuse. And so if you were to short together two of the battery segments in the packs and like in the board somehow, obviously you could like maliciously find a way, I'm sure, to short it after the fuses or something. But yeah, no, for the most part, it'll be directly contact with the bus bar and then immediately a fuse. So if you short something anywhere downstream, doesn't matter. The fuse will trip and you'll have to take out the PCB, which sucks, and then resolder the fuse, which sucks more. But it is possible. We have yet to trip the fuse. Yeah. Cool. Okay. Okay, so yeah, for like I was talking about, BMS board mounting, pretty simple. We had a little shelf, and honestly, that was fine. There were some cutouts at the top for routing wire through. That's about it. Yeah, so the big thing I wanted to say about the BMS shelf is like fine. Yeah, like basically the big thing is just like, as you can see in there, it worked fine. Like it doesn't really take any loads. So if you need to condense space, you can maybe make the shelf a little thinner or something. Like it doesn't need to be the given thickness. I think it's the thickness because of the heat set insert. Yeah, so like if you got crafty about, oh, you have like a fully sandwiched stack up and you found a way to constrain the bolt, then there probably could be other ways to make it thinner. You can investigate that at your own peril. Or, you could mount the BMS board in a totally different way. This works fine for us, but I know one of the things that I mentioned is if you're considering BMS sensing boards and BMS sensing connections as a more integral part of your pack, and if you are open to redesigning the BMS PCBs, it may actually be lower effort to design a new PCB that like has connectors that stick out the side, and then you send PCBs that just plug into them to avoid your wire. So there are potentially some ways to improve it, but like I said, overall, it worked pretty well. It was pretty easy. Don't worry about it too much. It's not worth being a whole project. Oh yeah, one of the things that we just straight up didn't know existed, but we invented our own one of, and then we're like, we are stupid, is we used a heat set insert, which is essentially you take a thing that has, it's like a threaded element and it has wiggles on the outside, and then you heat it up and you press it into some plastic with a hole. And then it goes in there and all the wiggles grab the plastic really well. And then you can thread into it, which is nice because you can now thread really robustly into plastic. No. So we do that only for mounting, like holding up the main board, because they don't want to. But yeah, anything that you're bonding to has seem to say that they are not. But once again, we should probably run that by them again because they seem to be totally McChillin with whatever. So, but what we realized is that we took a heat set insert and threaded and then put a bolt through it. You can just buy male heat set inserts that just have a threaded rod that sticks up. They're less common. They're like the normal heat set inserts are far more common, where it's like a threaded insert. But you can actually buy like heat set bolts that have an actual like thread bolt that goes up. We just didn't know those existed. You might not ever use one or need one, but those do exist. You have a separate tool that has a hole in the middle, and it. But like you can buy the tips for like $10. Yeah. Anyway, okay, cool. That's literally everything for the BMS board. We've already talked quite a bit about the BMS sensing stuff, so I'm kind of just going to skim through it because we covered a lot of this already. But basically, this is the ambiguous way that we connect the BMS boards to the actual like connections on the pack. like I highlighted, we have the actual voltage, we have temperatures, and we have cell balancing. Does anyone, not Joshua, want to explain to me what cell balancing is or why we need it? Fuck you. Not you either. Not you.
We thought we wanted to make sure that the voltages are the same. They're the same.
More or less, we do a slightly more rudimentary version that basically just makes sure that all of like once we get up to our peak voltage of 4.2 volts, we have some processes in place to make sure that once we are done charging, none of our cells have exceeded 4.2, and the ones that are a little slower to get there can still keep charging up, while the ones that are already at 4.2, we can dissipate that energy as heat. It's a
Maybe
little
not
more.
quite as rudimentary. But basically, yeah, once we're above a certain, if some cells are much higher voltage than the other ones, we just start something. And then the currents are all the same, but different. So,
That's definitely getting into like BMS wizardry, but the reason I mention is because on this particular BMS design, we have broken it out. So cell balancing and voltage sensing are separate things. And then you have your temperatures. There are many off-the-shelf BMSs that you can buy that will just make it one line and then it'll figure it out. The main reason that they like to avoid having them use one wire is because if that wire is being used to balance on that cell, there's current flowing through a wire. Current flowing through a wire, that wire has resistance. Current flowing through a wire with resistance has voltage drop. And that means the voltage you're monitoring of the cell that you're actively trying to balance, is now wrong. And you can't characterize the resistance of every single connection in the pack because all of them are going to be a little bit. So you can do this special thing where you like balance and then like turn it off and check the voltage and then turn balance again. You can like flip back and forth. And like there are ways that we can do that. And that's what Joshua was already planning on doing this year. Is that already enabled? Flipping back and forth between balancing and voltage sensing.
oh yeah.
Yeah, so like that's already enabled.
When it's balancing, when you call the voltage sense, it pauses balancing, it senses the voltage, and then it
Yeah, so we already kind of take steps. So there is potentially an avenue in the future for us merging those together into one set of connections, but that would probably have to be talk to Joshua, go full into the BMS and talk about exactly what would be the benefits, drawbacks, compromises, and issues with that code approach. Okay. Yeah, so like I already talked about, does voltage sensing, it allows for lower, ideally you want a lower resistance that you can actually do cell balancing effectively, blah, 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 blah. And then I already talked about the whole process of, we did this sketchy thing where we're going to spot weld the nickel strip and then solder a fuse onto that and solder a wire onto that fuse, blah, blah, blah. And then we realized that was stupid. And then we were like, oh, we can then epoxy a fuse to our bus bar and then solder to that because that's a little less sketchy. But then we were like, that's still pretty fucking sketchy. And that's where we got to the current PCB idea of saying, let's put a PCB on it and then put the fuse in it, which is still pretty sketchy, but it's less sketchy. But like I said, ideally that design would be matured more. So you could either have, maybe you don't need those sense PCBs at all, or because maybe ideally your bus bars could be designed such that the bus bar directly can connect with the BMS main board, or so the BMS segment boards would be awesome. But if that's not possible for whatever reason geometrically, because of how your pack is arranged, then yeah, you might have to have these boards, in which case ideally you would not have to make adapter cables and you would just have them plug directly in. But then your tolerancing gets super tight. So your pack has to be perfectly designed, which good luck. Okay. So yeah, wiring, soldering, all that stuff. Basically everything, all of the work that I had mentioned is that yeah, doing any work with the making wires and then epoxying all the stuff on just takes a really long time. And it's like putting extra effort into the design to make the design good, to make sure that you don't waste time during manufacturing, and then don't waste debugging effort during manufacturing. It's just better for everyone. So you should put that effort in. Now, that would probably fall more into the electrical side of things than the mechanical side of things, but y'all definitely should be coordinating at all times on that. Cool. You're already familiar with how these guys work. It sits on top of the bus bar. There's an electrical contact on the back of the PCB that makes contact with the bus bar. We use like a silver-based conductive epoxy that makes that good electrical connection and mounts it. And then we have temperature sensors that are connected at various points across the sensing boards. So we can actually go out and we can measure temperatures on the negative terminals of different cells. So now, quiz. Why do we measure the temperature on the negative terminal of the cell and not the positive terminal of the cell? No. No. think about the shape of the cell. Why do we measure the temperature on the negative instead of the positive? You're getting there. It is flat. Sure, you're getting in the right direction. You might know the answer, so I'm not. I prefer Dennis's guess.
It doesn't have both on it, it's only one of the terminals, because the other side has, positive and negative ring.
Almost getting there. Look at the physical geometry of the cell. What? The majority is the negative, yeah. What's up?
I was just gonna say that the negatives, like,
The negative is way bigger. That's true. You're basically getting to the right idea, and like I don't want to like harp on like, oh, you didn't say exactly the thing I wanted. Basically, it's the idea is that when you look at the positive terminal, it's not just like it bows out in that area. There's actually like a cavity underneath it, and so the positive terminal actually is like, for ours at least, if you look at it really in detail, you can see there's actually 3 little legs that stick out, and there's full fucking air gap underneath the positive terminal. And so if you're heating up the battery pack, there is like chemistry directly underneath that negative terminal that's getting it. And that will be a very, very accurate sensing of your full set, your cell temperature. But if you look at the positive terminal, you see the positive terminal, it has basically a plate that floats in the air. And so that means only those tiny little metal connections are getting all your thermal mass, all your heat up into that little part, which is not going to be nearly as accurate. And actually the rules literally say it has to go on the negative terminal. They're like, no, cannot go on the all right. So, oh my God, I came up with improvements for this. I already talked about this so much. I'm not going to repeat all of this. It's basically everything that I've already said. I'm just going to quickly read it to see if I left anything out. Plan from the beginning, include routing space. One thing that we did think about is I've already recommended don't use wires, but if you do have to use wires, don't just leave a space open in the PCB in the cell holders like we did. That ends up being a bad idea. If you want to run just like 1 or 2 wires, you can actually cut a little channel in the cell holder and it looks sick as fuck. You can cut a little channel that you can actually make exactly the width of the wire, and you can just press the wire into it and it'll sit in there perfectly flush. It'll be very cool. If you ever need to do wires like that, you can, but try to avoid wires at all costs. Lots of manufacturing costs, lots of debugging costs, not worth it. Oh yeah, like I already talked about bonding directly to the sense PCBs. Oh yeah, I already talked about this also. The big idea of if you could somehow redesign the whole segment to make it such that the BMS board natively is already just like touching each of the bus bars. I have seen at least one battery pack design where it was designed with the bus bars sticking off the top, and then the actual like BMS board directly went and like abutted against it and had little friction clips to clip onto the bus bars and detect them. If you are able to find, I don't know if you can find a picture of this online, it's pretty hard, but if you are able to find a picture of Carnegie Mellon sensing PCBs on their battery pack, it looks sick. They do this cool thing where they essentially have these 2 little cuppy boy springy mounts thing that actually cup onto the negative side, of all the cells. So they have basically a big cell holder matrix on the other side that's just a big PCB with a bunch of clips. And then you can just press it on and it natively clips to all the cells and to detect all of their voltages. And so they have one PCB that does everything for them. It has the built-in fusing, all of that, and it just presses on there directly. That's super cool and super sick. Someone can find a picture of it. It's really hard to explain. No, that's their normal beam. That's their actual BMS beam directly. Yeah. Basically, if you see a PCB that has a bunch of holes in it that has these little like silver clips that go and actually clamp onto the battery cells directly, it's pretty cool. If you can figure out a way to do that, awesome. If not, don't worry about it. That should sound really hard. Might not even be a good idea. And then yeah, just planning out your temperature sensor placement a little earlier. We kind of figured out the temperature sensor placement last second because we had a design, and then I was stupid, and then we revised the design, then we revised it again, then we went back to 1. And now we have our current design, which works fine. But ideally, we would have a good, well thought out temperature placement design from the beginning. So when you're designing your segment, you would also think, where can I place temperature sensors here efficiently? And is that going to fuck the BMS over? So cool. Maintenance plugs. Oh my God, I'm so excited. Basically, maintenance plug, what does it do? It conducts power from one segment to the next segment. And specifically, it has to be toolless. So that way someone can just come in and be like, shoobity boop bop, unplug segment. Particularly, you have to have maintenance plugs available to unplug both terminals of the segment. You can't just have like one that's permanently bolted and then another that's a maintenance plug. Both of them have to be unpluggable. They don't have to be. What's up? No, it makes sense. It's so that way you can, like, I get it. It's so that way you can make the segment fully removable without having. Yeah, you can disconnect both sides of it. Like, I get it. It's nice. They don't have to be in the same connector, from our understanding. So if they're not, but we do have the same thing. Since they're toolless, they're going to have some interface that allows you to remove them. Make sure when you're designing your segment, you think about, can I fit fingers into the area I need to actually unplug the maintenance plug? Because when we were working with our homies at good old Royal Power Solutions, no one cared to mention to us the fact that it would be literally impossible to unplug any of our connectors once they were plugged into the battery pack, because of the fact that we had two right next to each other, and the way that you're able to unclip them is like by shoving your whole finger in there, and they were going to be this close to each other. So your finger literally wouldn't have been able to get in to unplug these maintenance plugs. And they never cared to mention that to us. Now these ethanol ones that we're using, the Surlock Pluses, I believe, they just have a little button on the side. You press the button and it allows it to pop off or not. And we have them positioned in such a way where if they're out, the button is out far enough that you can very easily access it without. The maintenance plug also specifically needs to have like no exposed electrical connection except for the contact itself. And the idea is that they don't want you to just use like a fucking bus bar that's like down there. That's a good question. Cool. Yeah, it's a lot of stuff.
Shitting quality.
Yeah, yeah. We're not. This isn't the shit on Royal session though. Yeah, so the big things obviously that I already covered a little bit of is obviously it's conducting the full current to the battery pack, which means your options are very limited. Like if you type in like connectors that can handle, 150, 200 amps plus into DigiKey, you find like one or two options.
It's really annoying.
Yeah. Yeah, like there's not many options and they are quite expensive. Luckily, Amphenol was able to sponsor these for us, but it does mean on accident. We asked them for some, we asked them for other stuff. They said they might, or they probably won't be able to do these ones. And then we asked them like 7 months later and we were like, you haven't sent us anything yet. And they were like, oh, my bad. What was the list? And we just sent them the list of everything we wanted. And they were like, cool, we'll ship. And so we just kind of like sleazed, like $1,000 worth of connectors in there. Because I think they're like $50 a piece. And we have 16 of the maintenance plugs plus all the big battery connectors. So kind of, anyway. Yeah, I already talked about toolless, both terminals, some kind of retaining mechanism, which is just the whole point of it being tool. Basically, it can't be like a friction mount. So you can't have it just be like, oh, you slide it on top and that's it. There has to be like a button that stops it from being removed, or like a slide switch or something. And then like all connections in the high current path, it has to be positively locked when you bolt it. Who knows what positive locking is? One of you four. What do you not want a connection that keeps your battery pack together to do?
Oh, like knock one down so you can dialogue that.
That's exactly what a positive locking mechanism, yes. There are many ways that you can do positive locking mechanisms, only some of which are acknowledged by Formula SAE because they're weird. This can be everything from adhesive-based to something like Loctite, which Formula SAE does not acknowledge as a sufficient positive locking mechanism, to something like a lock nut, which is acknowledged, or something like what's called safety wire, where you basically can tie two nuts together in such a way where if one of them is going to loosen, the other would have to tighten. And so then as one tries to loosen, one of them will eventually stop it from turning. And just using this like cross twisting combination. But yeah, all of the connections in the high current path have to be positively locked in some way. And so we just use lock nuts on everything. Yeah, little nylock nut, no problem. He's dead. Obviously, like I said, our current designs were originally from Royal. had problems because they were low quality and also impossible to unplug, and machining them was ass. And so we migrated over to Amphenol Surlock Plus connectors, which are way better. Obviously, because of the fact that this is like a pseudo drop-in replacement, we had to like make a squiggly bus bar thing with some bolts to be able to actually make it happen. And they look like they're like as good as they can be, given the fact that we had to drop it in. But like it would be better if we could have just designed it from the beginning with these things and known that. But like hindsight's 2020. So now we very, very, very strongly recommend for all future maintenance plug stuff that you just buy something off the shelf and do not machine an existing part.
At all, even like cutting it into
because the main thing is that a lot of these parts are usually you'll have a piece of you'll have a contact, and then you'll have a housing that's like injection molded around it, and that means that housing is not intended to be heated up significantly or experience significant vibrations. And so if you do that by, let's say, machining it, you can cause that housing to very easily unmate from the contact, and then the contact itself. These ones have a weird interface where there's like kind of a friction mounting thing inside. You guys have seen one taken apart. Yeah. But ideally, yeah, never have to remachine a maintenance plug, and you would just use the thing off the shelf.
one thing to keep in mind, I think, with the maintenance plugs is if you switch to like ones like my thought is like ones that the ideal would be like the threaded ones.
Yep.
But the thing to keep in mind with that is that you never conduct current through threads.
Yep.
That like you should make sure that like I think with the threaded ones there's like a spot on the end where like you put the tighten it all the way down so that flat piece actually makes your electrical contact. Same thing with these ones, like the idea is that you should have like a flat base that conducts your current.
That actually gets into a really good idea to highlight here. Is one of the rules for all attractive system stuff, all battery pack stuff, all whatever, is that all current is only allowed to flow through things that are intended to conduct current, which sounds like a stupid rule, but it basically has a little italics comment underneath it that says, no, you cannot conduct current through a bolt and claim that conducting current through a bolt is like how you meet your current conduction spec. You have to have like a real copper or aluminum or whatever interface where you have it bolted together and the bolt is assumed to not conduct any current. Obviously it'll conduct some, but like, because they're usually made out of like some kind of, hardened steel or iron of some kind, you're generally going to get weird conduction properties. So just assume that it will not conduct. Inspect your cross sections accordingly. Okay, cool. Blah, 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 blah. Made some adapters, lots of wasted space. Okay. I have thoughts. I have super thoughts. Super duper monster thoughts. This is actually a thought that I thought about for the whole year, came up with no solutions because I'm stupid, and then thought of it when I was explaining it to you guys during the first meeting of battery knowledge transfer. Is that so we number one, don't try to make something custom. Louis already harped on that enough. Basically, don't try to modify something, don't try to make something custom, just buy something off the shelf and figure out how to fit it in your design, because goddamn, it'll save you so much time and so much headache. Because us making stuff is way more dick than us just buying something. Okay, cool. The big thing that I wanted to highlight here is this super cool idea of why are we wasting so much space in the top of our battery packs? Number one, to be able to, for looking at our current battery design, let's see, can I do is there like a pointer or something that I can?
Yeah, I think.
How do I do that? Mouse? Oh, that's useful. Spotlight? Oh. Okay, cool. There's my little cursor thing. I don't know, man. Anyway, yeah, so you have this idea of specifically syncing the plug and cabling into segments. So the idea that I really want to highlight here is if you think about this in our real e-box right now, this is like the top section of the e-box, where here and downwards you have cells, and then you have your BMS board right here, and then this is the metal contact portion of your maintenance plug, and then I guess how do I say it? There's like the the bolted part of your maintenance plug, and then there's the pluggy part of the maintenance plug. And every maintenance plug is going to have a similar structure where you have like a bolted part and you have like a pluggy part. Yeah. But yeah, so the bolty part and then the pluggy part. The way that we do this right now is we say, okay, cool, let's have our pluggy part stick up outside of the box. And then we can plug in the mating part on top. But then this presents you a problem. Our battery pack, as a reminder, has to be able to take forces in all directions, all 6 of them, including up. Don't ask. I guess you could roll the car and then hit a wall. 20 G's up? That's a hard ass bump, dog. Our spring rate is not that fast. Anyway, regardless, yeah, so one of the big things that I want to point out is that because of the fact that we need to be able to withstand forces in all directions, including up, down, we have to put in these, like, what do we even call them? Yeah, we put in these restraining bars, and the idea is that the restraining bar then can take load that goes from the cell holder into the e-box, and then take that and direct it up into the lid. Which, you know, from our current design is a very logical way that you could get force up into the lid. But what would be even more optimal is if we didn't have all of this space used, and then we didn't have to put in big pieces of metal for our restraining bars. And ideally, we would actually have a chunk of the e-boxes directly where we could take these plugs, sink them inside of it, and then you could have the bolty part and then the pluggy part with the cabling and all of that in here. That would be super great. And the reasoning is because now that means that you could fill cells all the way up to here. You could fill cells all the way up to the top, and then your e-box and your cell holder could go straight all the way up to the top, and then that could apply forces directly into the plate. So you're wasting a lot less space, a lot less air volume. But you can see how this makes your segment design way more fucking complicated. No longer can you do a rectangle with plugs on the end. Now you have a rectangle that's squiggly at the edges that has plugs on the end that are also sunken in. And also, oh, by the way, if you do 2 of these segments, like let's say you do one segment and then another one stacked out of the screen, if this is the positive terminal, this has to be connected to the negative terminal of the next one. You can't just design them however way. You have to make sure that the voltage is continuously increasing as it goes back and forth.
One thing, I think, just for clarification, for the way we have it on the left is like the little restraining bars, the little dark gray squares are welded to the lid of our big steel container that all of the batteries go into.
Oh.
And they're basically, they just kind of sit right here, and they have like foam on the bottom, such like it keeps the lid down basically. So when you put the lid of the big steel box down, it has little bars welded to it that just keep the lid pushed down.
Yeah. So ideally, if at all possible, it's sort of in this effort of saying, hey, how can we actually reduce volume? How can we make packaging and mounting easier? Ideally, we would migrate to this trend of saying, hey, let's try to merge this into the e-box. Showing what this would look like in a little bit more resolution, you can imagine that it's like, you would have, like, let's say you choose to stack your cells 6 high in this random configuration that I've selected. You would have your cells that are all stacked up. Let's say you have another plug on the other side that's off screen. What you'd imagine is that you'd say your BMS is somewhere. And then specifically the plug that connects data, that connects the big power in and out of the actual segment, you would have this bolted part on the inside. The pluggy part would still be outside of the e-box, except your e-box would now have a weird shape. That means your e-box manufacturing gets more complicated, which is not necessarily great. But it means that now your space usage in the pack is going to be significantly more efficient. And then that would be sort of a topic of discussion, option of saying, hey, how much space do we actually save if we do something like this? Because from my interpretation, if you want to use an off-the-shelf maintenance plug, the answer is a fuck ton. And those bitches are tall. So ideally, what you would do is you would be able to use an off-the-shelf plug, and since they're super tall, you'd be able to sink it into ideally the end or the side of a segment. Sink it in there, and it basically consumes the same amount of space. And then the idea is that when you have to do your force loads to say, okay, this applies loads and whatever around our battery pack, the idea is that you could have cell holder that's going around basically the entire edge of the e-box. And so when you apply a force in this direction, it hits this wall directly. A force in this direction hits this wall directly. And a force in this direction, you would just have to make sure that this like cell holder going through all of this area is sufficient to take the load for the whole site. So it's, it's going to probably experience a bending moment. So you might have to do some special chamfering stuff. But I think that this could be a way to improve your volume. If you can come up with a better solution, do that instead. Your recommendation. Because these are all steps that could be taken to just like save space, save space, save. You both seem like you're deep in thought.
Like how you actually an actual plug.
Yeah. So for example, this does it in a kind of weird way that it says rather than us making it a shape that we want, it kind of smooshes it in a weird, because essentially what ends up happening is that our angle of the firewall is so different from the 60-degree angle of these cells that it doesn't matter if we stick more shit near the bottom. And so we use this to make a box that can sort of stick around the outside. And it can get closer to that 45-degree angle. It's still not anywhere near it, but it sticks out more because this would be even more upright if those main employees weren't there. And so this is one of the designs that I like put together as a demo, saying like, hey, given the stuff that we've learned, what would a new design potentially look like? And this is one potential option is your maintenance plugs are down here at the bottom. You stack your cells in this weird configuration. We've got a squiggle at the end, but then it does it in basically like a this kind of shape. Trapezoid? Don't ask. I don't know. I made it quickly in Onshape, and in Onshape, when you make a bunch of new parts, it auto assigns them random colors. This is just a sketch. So obviously, this is just like an example. If you want to, on the slide deck, it links to the actual Onshape design because SolidWorks dies on my laptop. So if you want, you can feel free to open it and look at it. And use it as inspiration, but not your real design, because the fact that it's an Onshape. We do designs in SolidWorks. You're engineers. I'm not an engineer. Sure. But yeah, so this could be one potential example where you would then your whole maintenance sorry, you would do some special stick out. So you'd actually sink it into the side. But yeah, this doesn't even fully take advantage of that. Like, as I designed this before I came up with the idea, but you could even sink it in more, where you could say you could completely take this and just fully suck it in there, where it's just completely sunken. They just have to be accessible. So like whatever is, so if you design the pack such that there's like a lid that goes on the top, then you'd have to ideally put them on the top to make it so you can unplug them. That's you can't take that. But it, you don't. If you can take the whole thing apart and the box just moves like that, then cool. Cool. Oh God. Do we want to start cells or do we want to call it here for today? Because I know you have to run. Cool. So I'd say right now, unless there's any other questions, we'll call it here for the day. I think even though we didn't get through many slides, we had a bunch of great discussions, which I think were awesome. And we'll this back up same time next week. Yes, sorry, but yeah, at 5. At 5 again next week. Yeah. So any other questions? Great, a lot of great conversation, a lot of great questions today. Obviously not as many slides were covered, but that's fine. And as a reminder, if you ever want to, you can always look through the slides. You can go back through them. If you take any notes that you think are valuable, please feel free to add them to the slide deck. This isn't my child. You can just put stuff in there. So anything else? Any thoughts? Cool. All right. Thank you very much, everybody. Have a good one. Bow. That means one. A bow. Bow. Mm-hmm.
Find it like a cute little thing.
Cool. Okay. Yeah.
He said that.
Yeah. I mean, obviously, I do the recordings for all of them. So yeah, if you if you end up not being able to make it yet, just let me know. And the recording's always available. Yeah, come in person, everybody. Makes me sad that no one shows up to these, except for this, except for these valiant individuals. We appreciate them. These are your next generation of battery pack design. Anyway, thank you, everybody. Let's get into Pt.3.